Hello, for today's video lecture we're going to be talking about impulse and momentum in rigid body systems. So as we've seen before, when we move from a particle system to a rigid body system, we'll not only need to deal with forces, positions, velocities, and accelerations, but also the rotational counterparts. So we need to deal with moments, orientations, angular velocities, and angular accelerations. In impulse momentum, particularly the moments and angular velocities are going to be important. So this remains the case with impulse momentum. We add those rotational counterparts to the translational parts as well. So we can still use the stuff we've used with particles, we just have new stuff to add to this now. So we expand our equations. Our original impulse momentum equation was J equals mv final minus mv initial. That was the impulse on a body is going to be equal to the final momentum minus the initial momentum. Now we can relate the angular impulse, so K is what I'm going to use for angular impulse, and that's going to be equal to the final angular momentum minus the initial angular momentum. So this can either replace our impulse momentum equation or it can supplement. We can use both of these equations in certain problems. All right, so let's talk about the impulse or the angular impulse of a moment. So the impulse of a constant moment over a set period of time will be equal to the magnitude of the moment times the duration of the time. So m times t is our k, and more generally the impulse of any moment, which may change over time, is equal to the integral of the moment over that set period of time. So just like we can integrate the force function over time, we can integrate the moment function over time to find the angular impulse in this case. So in addition to magnitude, the impulse is also going to have a direction. So assuming the moment has a constant direction, we're not going to do anything too crazy in this book. The direction of the moment is simply going to be the direction of the impulse over that time. All right, for angular momentum, the angular momentum of a body at any given instant is going to be the mass of the body times, or sorry, the mass moment of inertia of the body times the angular velocity of that body. So we take the mass moment of inertia, I, and we multiply that by the angular velocity. That is our angular momentum at any one time. So this can be taken about a fixed axis of rotation, or it can be taken about the center of mass of a body. So generally we're going to do the fixed axis rotation if that's an option. If not, if we have general planar motion, we want to use the center of mass of our body for this angular momentum. And we want to make sure we take, the most important thing is we take the moments and the mass moments of inertia about the same point. So if we have moments about point C for the impulse, we want the mass moment of inertia about that same point C. So the angular momentum is going to have a direction as well. So in this case, the direction of the momentum will be equal to the direction of the angular velocity. So if you kind of think about the angular velocity vector, the same vector is going to be this, or the same direction of that vector is going to be the direction of the momentum. All right, so with different types of problems, we might see different types of pieces to this. So first is going to be fixed axis rotation. So if we just have fixed axis rotation, we are rotating but not translating. We're going to use the rotational impulse momentum equation, balancing the impulse with the change in momentum. So we would just use the k equals I omega final minus I omega initial. That is, the impulse is equal to the final momentum minus the initial momentum. And it's important to note that if a body changes shape, it's also going to change mass moment of inertia. So we didn't deal with this too much for the linear mass moment of, or the linear impulse momentum equation, because it's hard to change mass, but it is easy to change shape. So if we imagine like a figure skater, if there's no impulse, assuming she is spinning here, if she pulls her arms in, it's going to decrease her mass moment of inertia, and in the absence of that angular impulse, the final angular velocity has to be higher if the final angular or the final mass moment of inertia is smaller. So it has to balance out in the end. So do be aware of that. The I don't have it listed final and initial here, but if we change the shape of a body, we will change the mass moment of inertia, and we can use our impulse momentum equations to relate the initial and final angular velocities based on that change in mass moment of inertia. All right, so moving on to general planar motion. So when examining a body that's both translating and rotating, we can use both the translational impulse momentum equations, or use the the translational impulse momentum equation. So we can still break this down into x and y. And we can also add in the rotational impulse momentum equation for a third equation here. So this is similar now. We have forces in the x, forces in the y, and moments. Here we've got impulse in the x, impulse in the y, and angular impulse for these three pieces. So it is important in these cases that we're going to want to use the velocity of the center of mass of the body. We also want to take the mass moments of inertia and the moments about the center of mass of the body. So these velocities here are all going to be about going to be the velocity of the center of mass. The moment in the k value, so that is the angular impulse, is going to be about the center of mass. And the mass moment of inertias, I, before and after, are going to be about the center of mass. So that's going to be important. We don't want to take the mass moments of inertia or the velocities of other points in our system here. All right, so reviewing the whole process for this, we want to kind of carefully account for everything in our initial and final states. So we've got momentums before and after, and then the impulse that happens in between. So step one is you want to set up a diagram showing the initial state and some other final state. So we want to identify any external forces or external moments that are going to act on the body between the two states. It's going to be related to our impulse. We want to identify the known and unknown velocities and angular velocities at each state. We are going to want to put together, using the diagram, we want to put together our equations. So we've got the translational impulse momentum, so J equals mv final minus mv initial. That can sometimes be broken into x and y pieces. We have got the rotational piece, so K is equal to I omega final minus I omega initial. And sometimes we will also want to relate, so sometimes we will need to relate something like the angular velocity and the linear velocity if we've got something like rolling without slipping. So we might need to kind of slip some kinematics in there as well. And then once you have your equations, make sure you've got enough unknowns. But if you've got enough equations to solve for all your unknowns, simply do the algebra, solve the equations for any unknown quantities. All right, so that's all I have for today's video lecture. Thank you for watching, and I hope to see you again.